Okay, let's get going then. So again, a very warm welcome to you, and thank you very much indeed for joining us again today. This is the second part of the reaction monitoring webinars. The first part was given 3 weeks ago, and if you joined us for that, then fantastic. Thank you, and thank you for that. If you had perhaps you didn't have a chance to or weren't able to join us and you had to go and look on YouTube to find it, that's absolutely fine. We'll do the same again with this video, so you'll have a chance to review this. I'm going to go at quite a fast clip today because I'm going to assume that you've had more than your kind of introduction that we did last time, and so I'm going to assume that you've got a little bit more familiarity with reaction monitoring, and so we can go through. So if you recall, I spoke about the reaction monitoring plugin as being something that gives you access to the building of graphs of concentration versus time, which is what you want to have if you're following kinetics. And we had some questions last week about how to use the initialization of the concentrations and so on and so forth. And I did write a little blog article on that, which you'll find on the Mestre Lab website. If you can't find it, let me know. It's also linked to it. There's a link to it in LinkedIn, and I'll also try and touch on some of those today as well, just so that you can see that those in action a little bit. So it's going to be a little bit random today. I'm just going to pick on little subjects and show you some data which are, sometimes good for displaying certain bits of the functionality that we have in the software, and so yeah, a little bit random, but hopefully you'll enjoy it, get something out of it, and it'll be time well spent for you. So let's crack on then. And the first thing I wanted to do was to bring in the good old ester hydrolysis data, which you've seen many times now, but that's okay. So let's do the import spectral stack. So ester hydrolysis. Right, so one thing I want to talk about is alignment. So what you'll recall is that we looked at data like this, and it's not uncommon at all to see spectra whose peaks wander slightly with time, or sometimes wander considerably with time, several parts per million. This can be, in the case of this data, it's a consequence of pH change because it's in water. In other cases with organic solvents, it can be a consequence of protonation and deprotonation. But this is not an uncommon occurrence at all, so we need to look at ways in which we can deal with it. And we spoke about, and I showed you some ways, well, one particular way, which is to draw an integral region that you can move around. So we have the wonderful little green snake that you can thread your integrals through, if you recall, and I'll show you a few more of those today as well, because I want to make a few other points about that. But I also want to talk a little bit about alignment, because that can sometimes get you around the whole problem. So if you have a whole data set like this one, where all the peaks are moving at the same rate, then you can maybe consider doing an alignment process to help you. So if we think of global alignment, we have essentially two forms of alignment. One is a local alignment, which means, let's say, all the peaks in the spectrum were basically fine except for one particular multiplet which happened to romp around the spectrum. You can then do a local alignment on that one multiplet that's moving, or the global alignment applies to all the peaks in the spectrum. So let's see, there's essentially two ways to do it that I'm aware of. The first is and probably the easiest, is if you have a nice reference signal like TMS here, what you can do is come to your referencing, which is here. Click on the TMS of the first spectrum. I notice that this is misreferenced. I'm going to put that at 0. But the important thing is that you see here there's a box to tick called auto tuning, and you can give it a range. So within 0.1 ppm, I'm going to ask it to align the spectra for me. So it's going to go quite quickly. So I'll just move that off and I'll click OK. And there you go. Those are all aligned. And when I go back to the other peaks rather, these are the ones that I've been looking at. You can see that these are nicely aligned as well. And these are nicely aligned, and so on through the spectrum. So it's a bit easier now to come in and there you can see them. Oh, maybe a little bit messy, not too bad. So it's quite easy now to come in and set your integral limits to a sensible range without having to fiddle around with the handles and move them to accommodate the moving of the peak. Right. The second way to do that is if I close that and I re-import them. Second way to do that is to do it on a multiplet itself. So let's pretend that we want to do a local alignment. So let's say we'll start with this multiplet at 1.4. It's actually not 1.4. We need to reference it, which I'll do quickly. Right. Okay, so we're going to do a local alignment this time. So processing, advanced, processing. Where's it gone? Align spectra. So okay, so this time I'm going to do a local alignment. So I'm going to add a region manually. I clicked on the button with the plus on it, yeah. And now I'm going to drag across that guy, and I'm going to ask for a preview of the alignment. It's going to calculate it now. That's done it. You can see some little areas where it's a little bit funny, and what it's had to do is to pad those with 0 data points, so to speak. So if I'm happy with that, I can click OK, and then it finalizes that for you. And so you'll see that this one's nicely aligned, and those ones are, as before, not very well aligned. Okay, I think that's all I'm going to say about alignment, but it's certainly all I'm going to say for now. Now, let's go ahead. I want to talk a little bit now about the time increments. So you'll notice that when we do some calculations, it's the time points are filled in. And we do our level best to get those right, but they aren't always right. So we need some ways of fixing that. And I'll show you how you can customize that for yourself in case Mnova gets it wrong. Okay, so let's create an integrals graph for the fun of it. Integrate that guy. Okay, it's taking a long time because it's using a different integral method, which I'm going to speak about a bit later, but that's okay. Right, so it's done the integrals. It's done actually a GSD integral here, which is why it took a little bit longer. And I will talk more about that later. But what I want to ask you to focus on at the moment, please, is this column here, xi, which is for the x data points, which is time. So you'll see that the first data point is at 10 seconds and 750 and so on and so forth down the series here. And it may be that this is all wrong. So well, how do we fix it? Two ways to do this, basically. The first is to apply kind of a regular expression that we can use. So regular expression that might use the index. This is the index I, 1, 2, 3, the row numbers. If I click on this array data I cell, you'll see that this little 3 dots, these little cell with 3 dots pops up. And if I click on that, then you see that I get a new box. I hope you can see that. I can't resize it. And this is where I can actually change it. So I'm going to create a hypothetical. I'm going to say, actually, the first point wasn't acquired for 5 minutes after the addition was made, and then I want to say that there were 740 seconds between each data point. So the way you would do that would be to go to away from this array data. Just uses what's pulled in. If you go to something below that, or you can create something below that, I can do something like 300 minus I minus 1 times 740. So what have I done here? I've said that the first 5 minutes, 300 seconds, is to be taken off, and then I minus 1 is the index, so that's the 0 index times 740. Let's see, I should put minus 300 at the end, shouldn't I? Let's try that. There we go. So that's a manipulation of the time axis using the index and whatever you like. So let's take away that 300. I don't like it. So I should have put a bracket there. Okay, well, enough playing with that. You see how that goes, basically. The second way of playing around with the time indices is to import them. So let's say that we've gone ahead and created a nice spreadsheet with the data. So here we go. What I've done is to simply created the first 15 data points are separated by 2 seconds, and then the ones after that are separated by 5 seconds. So you may have portions, what I'm saying is that you may have portions of your data which are acquired at different time intervals. So what I want to do is to select all of those, and I'm going to copy them, Control C, and now I'm going to go back to my graph here, Data Analysis Panel. I'm going to click on the top cell, and I'm going to paste. And what you can see is that it's pasted in the numbers from the Excel spreadsheet. Now remember, I changed the interval at a certain stage, and that's why there's a kink in the data here, because that's obviously not correct. So this tells you what it's doing. Go back to the original. There we go. That makes more sense. Okay, I hope that makes some sense. You've got two ways of changing the time points. You also have a way, various ways of changing the first time point. So it can be that you decide that your first time point is over there. If I right-click on that, I can select Use as Time Origin, which will blank out the first two of those and make the third row as time equals 0. Okay, so there's quite a bit you can do to get the time equals 0 correct and to get the intervals between the data points correct. Okay, I'm just looking at my notes here. Okay, that's it for that data set. Let's move on to some enzyme kinetics. I should acknowledge Tim Claridge at Oxford for kindly sharing these data with me. Right, so let's see, we've got enzyme reaction. What I want to show you in this is another way that we can get the concentrations right. You'll notice that I've got concentrations here nicely for some of these guys. And I also want to show you a little bit about how to determine initial rates, how to change the region that's used or the region of the build-up that's used to determine the kinetics, so the fitting curve, that is. Okay, so let's do a little bit of baseline correction, I think, on this one. Done. And the peaks I'm interested in are around 3.0. Yeah, it's these two over here. Okay, so this is the reactant. If you recall, if I go to the, I'll put that on the spectrum, you can see that this is the GBB peak, this guy over here, and that's 40 micromolar. Now you can say, if you look at the spectrum, you can say quite correctly, well, if I do the initial concentration on this peak over here at 3.06, it's actually started turning over, and there's actually a little bit of this already. So the concentration represented by this area is not actually 40 micromolar. It's a little bit less than that because some of it's already gone to product. So one way to get around that is as follows. So now we're going to do advanced data analysis, create concentration graph. Where's it gone? Oh, back. Create graph. Oh. Bit weird. Here we go. Right, so as I said, the problem we have is that, oh, this is annoying me today. Let's grab this and put it, it's automatically docking all over the show. Let's just dock it on the side here. Right, so what we want to do is to say that the sum of the integral of that peak plus that peak both add up to 40 micromolar, basically. So what I'm going to do is I'm going to go along here to concentration, and I'm going to draw a big old region like this that spans both of them. Now I know that I think this is one nuclide. I can't remember, to be perfectly honest with you. Index 1, spectrum 1, and this is 40 micromolar. Okay, and that should be relatively constant across the spectrum. Okay, now just close your eyes for a second. I'm going to change something, and then we'll have a look at it again. I need to reset this. As I said, it's doing, so I've set it to do sum integral again, which is the standard way. So these values are all about 40, as you can see in the data analysis panel, which is what you expect. And I'm using this really as just a kind of a calibration, so that all the other concentrations that follow from here will be correct at 40. So now I can go in and I can add this guy, got 1 nuclide, that guy, product, 1 nuclide. And you can say, oh, this is pretty messy, I've got all these things overlapping. That's not a problem. I'll select the first one. I can say, I can make that invisible. And although it's visible on the spectrum, it's actually invisible, if you like, on the plot, which is the important thing. So there you can see your build-up curve for your product, your consumption of starting material. That's all well and good. And another question that I got last week at the end of the seminar was, well, what happens if you want to look at initial rates? What happens if your kinetics is only important at the start of the reaction? Well, there's a way that we can do that quite nicely. If you look at the build-up, if you look at the curve here, you'll notice on the right-hand side and on the left-hand side there's an unfilled red box. Now that's a drag point. I can click that and drag it along. You can see I've dragged it to about 600 seconds, okay? Let it go. And you can see what it's done now is it's excluded the points to the right. These are the ones in the gray region. To the right of 600 seconds, those points are now not being used for the fit, and only the points on the left-hand side here are being used for the fitting. And so this might be something like an initial rate determination. And in fact, if you look at the fitted line, which is the red line, you can see that it starts deviating from the data points as we get to 1,000 seconds and so on, outward this way. So it would be an extremely reasonable thing to do. And where you choose to set this point is up to you, really. You can move this around dynamically and change things, and the fitting will be recalculated automatically as you move that. Now, it's not relevant to this data, but if you had data points at the start of the time course that you wanted to exclude, you could do that by removing them from the left-hand side in that way. So you can control it from both ways. Okay, I hope that helps you guys doing enzyme kinetics. Okay, let's get rid of this. Let's come back to the full spectrum. So another way that you can determine concentrations is from an internal standard. So if it turns out that you have something in there whose concentration you know, perhaps a buffer signal. Here we have something that seems to be constant through the course of the reaction, so I'm going to assume that that's nice. 1.19 to 1.16-ish. My region was 3.1.19 to 1.16. There we go, that's what I want. So I can create a new curve like that. And rather than an initial concentration, I'm going to say there's an internal reference. Beg your pardon. I need to do this on the internal reference, so let me cancel that. Sorry about that. Let's come to this little peak over here. I'm going to do concentration, and I'm going to say that this corresponds to 10 micromolar, for example, and that's worked that out for me. And now that's how it's now worked out the concentration conversion factor, and everything goes smoothly from here. So now it does, when I ask it to look at one of these multiplets, singlets, it's just going to ask me the number of nuclides. So there we go. That's another way of doing it. And as before, you can make the line from the first one invisible, like that. Okay, I think that's all I had from the enzyme reaction. So let's move on and pull in some data from an imine reaction. So import right, what I'm going to show you is a global alignment to reinforce that with you. Okay, there's actually quite a bit of overlap with this data set from what I showed you in the first data set. So I'm going to whip through it really quickly, and this will be a reiteration. Now, there are softwares out there that try to automatically track peaks that move, and it's a worthy objective. It's I think going to be quite tricky in some cases. I'm sure in other cases it won't be that tricky, and well, I'm sure we'll do something in those lines as well. But I wanted to make the point that there will be cases always where a manual tool to do the alignment is important to have, and this is shown in this spectral data set. There we go, it's done. Oh, no, it's not. Oh, goodness. I need to make smaller data sets, don't I? Just as a point of, just to make a point that when you're doing these reactions on organic matrices or organic type reactions, and when you do have the luxury of time, it's not uncommon to collect large data sets, perhaps with a couple of hundred elements to them. So this one with about 100 in it is not unreasonable at all. I think the enzyme kinetics ones tend to be a bit smaller because they're generally done at lower concentration. So here we've got lots of things moving around. As I said, we've got some initial points that I need to get rid of. So let's zoom in on an area like this. So a couple of points. Notice that the first 4 or 5 spectra, so these spectra were acquired using a reactor. So it's one of these flow-through reactor type systems. And at the beginning of the experiment, things are a bit strange and moving around. So how do we integrate this type of stuff? You'll notice that in this region here we've got things overlapping big time, and I think that to automatically analyze this would be a bit of a challenge. Okay, so as I've said, you can create a smallish, I'll leave that as is, a smallish area like that, and you can use these handles to move things around so that they I put it to you that having an algorithm that reliably works this out for you would be quite difficult. I can grabbing a bit of intensity from that there, so I'm going to squeeze that in a little bit like that. Okay, so that's to show you that. And just to come back to what I showed you before, what to do when alignment is a major issue. This is the acetonitrile peak, and you can see that that's shifting around all sorts during the course of the reaction. So if we go for the global alignment, it's going to mess up this curve, so let me delete it. But what I wanted to show you is that if I do align spectra and I choose the region around here, around the acetonitrile, and I click on Apply Global Alignment, you see it here. It's actually going to perform that for us straight away, and that's pretty decent. So I click on OK. Now it actually does it properly. It's done, and everything in the spectrum now is nicely aligned, and it would be far easier now to go in and select regions and do what you need to do. Okay, one more data set. Let's go for it. Okay, this is a bit more challenging. Again, I think there's quite a lot of data in this one, so, oh, no, that's pretty fast. Okay, so we've got some things that, what we've got to do here. Well, we've got some phasing issues. This is done, it's reaction in presence of unit space, and I think there's a saturation that's been done at 4.7 ppm. Okay, so let's say we're not too happy with the phase, and indeed around this peak here it's perhaps not that great. So autophase, how does that work? So if I go to, this is intentionally not going to work, so here we go. So processing, phase correction, automatic. Okay, it's done. As I said, it hasn't done a particularly good job. It's gotten confused, and there's a reason for it. The reason is that horrible spike. So I'm going to undo what I've just done by clicking on the undo button. Yeah, and we've got this horrible spike with random phase around here at 4.7 ppm, and that's messing things up in terms of the autophase. So what we need to do is to mask that region and ask the autophase in essence to ignore it. And the way we do that is by using blind regions. So blind regions are important when you have anomalies in your spectrum, or perhaps when you have very big peaks that, well, anything in your spectrum that you want ignored basically by an automatic routine. So I'm going to come to View and Blind Regions and, sorry, add a blind region, and I'm going to essentially chop out that bit there. Okay, so that's that horrible point where there's saturation of the peak, and now when I come to processing and phase correction automatic, it should do a better job. Okay, now I'm not going to say that that's a perfect job, because as you can see from this peak at 6 and a bit, it's not phased brilliantly for the last one. If you had one data point, one spectrum that wasn't well, or a couple, let's say the last couple were not correctly done, I'm trying to select a few of these. Alt, Shift, and click. Right, I press down the Alt key so that I'm selecting spectra. I press the Shift key so I can select a range, and then I clicked to select those last couple of spectra. And if I now go to processing and manual correction, I can manually adjust the phase of those selected spectra. Those active spectra, the ones with the blue in them. Okay, it shows on the first spectrum, but it's applied to all of them when you let go. Okay, so let's clear that selection, and so we introduced a baseline problem there, so let's fix that. There we go. Okay, so that's clearing up phase problems. So let's see now. So again, I come to this point about selecting regions. If you wanted to integrate these three regions here, you would certainly need something better. An automatic tool wouldn't work for you. But I also want to talk a little bit about different ways of integrating. And although these data aren't perfect for illustrating it, I'll do it anyway. So let's say we want to so a common case might be that you've got two peaks that are very close to one another, and you want to accurately integrate them. How can you do that? If you do the normal integral, then it could be that a tail of the first peak goes into the second peak. This might be the case, for example, especially if you're running in protonated solvent. But that's not the case here, but I'm illustrating the point for you. So I think we can probably do some global correction here. Should we do that? Of course we should. So align spectra, add this region to the global alignment. Hasn't done a wonderful job. Okay, that's pretty rubbish, isn't it? Right, so I did want to say too that alignment is quite tricky, just as which is the point I was trying to make with when you're extracting a multiplet that's moving, that's essentially an alignment issue, and alignment can be quite tricky. It's obviously failed in this case, so not a bad lesson learned. If it can fail, so let's undo that, and we won't do alignment on that peak. Why it fails can depend on cases like, in this case I've got a doublet, and it would work better with a singlet, which we can try. So let's add a region here. I think I may need to hope this works better. No, it didn't. Oh dear, that was awful. So let's cancel that. Okay, I'm not going to do any more alignment. I've learned my lesson. Right, I wanted to talk about global integration versus sum integration. How do you do that? Well, the way you do that is to set the integration method. So if we go to Analysis and Integration and Options, yeah, I might have missed it. I did. Okay, so the option window pops up, and you'll see that the calculation method for integration is set to sum. What that means is that it uses the traditional method of integrating a peak, which is to basically sum the height of all the points throughout the peak, throughout the peak. And that's all well and good. But there are cases, as I say, where you'd rather use GSD, Global Spectrum Deconvolution, to perform your integration, because that will allow you to integrate accurately or reasonably accurately peaks that are quite close to one another. So what I'm going to do is I'm going to change it from sum to peaks, and the peaks it's going to use are all of them, and I'm going to click OK. Now the one other thing you do need to check, and this is almost always by default it'll be right. If I go to Analysis, Peak Picking, Options, you need to check that it has GSD here and not standard, because you could go back to sum integrals if you weren't careful. And we can click on defaults. I don't need to classify, so I'm going to turn that off. And now when I create a kinetic experiment, concentration graph, any graph really, I select the area, well, the integral region, like that. Doesn't matter. It's actually going through and doing global spectrum deconvolution on each of those regions for each spectrum, and it's come up with that curve. How well does that compare with using a sum integral? I mean, this is a case where you don't actually need GSD, but I've used it just to show you that you can. So let's create a new graph and compare them side by side. And I'm going to do the same thing, but now I'm going to go back to using sum integrals. Okay, sum, normal, and let's, oh, I don't think I did a great job there. Let me do it again. There. So those are roughly equivalent. You could argue that there's probably a little bit more noise in the data points. So yes, the GSD may not give you quite as accurate an integral as the sum integrals, but it can be applied in cases where sum would clearly fail. So I apologize that this isn't a brilliant example of it, but I'm sure you can think of cases where that would be a problem. Okay, folks, so I've basically come to the end of what I wanted to talk about today. Last time I spoke to you, I mentioned under the reaction monitoring button here, we've got the listener and the wizard, and I showed you how you can go through, and the wizard steps you through the whole analysis. And I said that I'd go through it today, but I did actually wind up going through it a couple of weeks ago. Remember, you've got the load and save settings here. You can choose your import directory over here. This is all stuff that you know. Go to the next window. You can choose a processing template if you'd like to. And then we zoom in on a region. We don't get the option to set, see here, Control plus space to zoom, Control space bar allows me to zoom. Go back to the sky. and I can now integrate that region. And it does that for me, and integrate this guy. Does that for me. Go to the next part of the wizard, the next window. What kinetics do we want? What fitting do we want to use? We can ask it to use the best fit, which is based on reaction order. Let's leave it at that, let it have a go. And we can ask it if we want to report, and we can save files if we want to, finish, and there we go, all done. And the listener, as I say, I'm not going to go through these in detail today. I went through them last time. The listener is all about creating a folder where data get added as time goes by. Processing is applied, and then an equation is used that describes the event that you want to see and what you want to have occur when that event is reached. So in this case, the concentration exceeds 7. A message is popped up with that in it, and a command line execution is triggered with that in it. And I'll leave it at that. You guys saw it last time. Have a look if you want to. This is great if you want to do at-line reaction monitoring and have it control things. And I hope that you can see that both of these, both the listener and the wizard are some things that you can, which are quite easy for the average person or perhaps an operator to use. And so it could be deployed in an environment when where there isn't, where you aren't around and you want perhaps a less skilled person to operate this stuff. Okay, so that's the end of what I want to talk about today, and I'm going to ask Ollie to tell me if there are any questions that you've. Any questions? I don't see any. Okay, no questions. So thank you very much indeed for joining us today, and I hope that this has supplemented the first reaction monitoring discussion and given you a bit more information, and hopefully now you can go ahead and do more complicated things. As ever, there's yet more that could and should be discussed, and as ever, as I've always said, you're very welcome to contact me directly at mike.mestrelab.com, and I'll be very happy to try and answer your questions, specific questions. So good luck with your work, and do let us know about your successes and so on and so forth. We'd like to see that, and I'll see you